Hello, and welcome back to another video with me, Elizabeth Bishop, your Autodesk Certified Instructor. In today's video, we're going to be looking at the simulation workspace in Autodesk Fusion and how we can use this to perform thermal analysis to model thermal problems with our models. This might be something like cooling fins or looking at insulation. We're going to be looking at this pipe and determining if the materials chosen are suitable for the thermal situations it'll be operating under. So when you're in Fusion, we're normally working in our design workspace. In order to perform a simulation, you need to move from the design workspace into the simulation workspace. When you first move into this, it will open up and ask you what type of study you would like to do. For this one, we're going to select a thermal study and click Create Study. As always, we want to work from left to right along the top. There's nothing in this model that we need to simplify because we want to use everything for the simulation. But if you did need to, you can head into the Simplify workspace and simplify your model. We can see here that the default is to use the same as model in our study type, but we want to change these. So you can select from the Fusion database the types of materials you'd like to use. I'm going to find a copper for the inner pipe, so I'll use a copper wrought for that one. The middle layer is the layer of insulation. I'm going to find a polyurethane foam for this. So scrolling down to the bottom and looking for polyurethane foam. There we go, the polyurethane foam. And then finally, the outside layer is going to be ABS plastic. When you're selecting your materials, you can open up the property box. And the one to look out for is the thermal conductivity here. So we're interested in the conductivity of the different materials. And you can switch between those to view the different properties that we're selecting here. When you're happy with your materials, you're going to select OK. And we can see that the interface updates to reflect those material appearances. We'll now apply the thermal loads. So thermal loads can be added to entire bodies or to individual faces. There are different types of thermal loads that can be used to establish different boundary conditions, and it's possible that a face or body might have more than one type of boundary condition applied to it. For the first load, we're going to use an applied temperature of 95 degrees Celsius to represent the temperature that is applied to the inside of the metal pipe from the fluid or gas running through it. Because metal conducts heat and the fluid or gas in the pipe is in direct contact with it, heat is transferred by conduction from the fluid to the metal. So in order to do this, I want to select the inside face of all of the pipes. I'm going to open up my model components here and hide the middle and outer pipe to help me find those surfaces easier. Selecting the inside there, and then the third one is a little difficult to get to. So I'm going to press and hold and then select the alternative face to make sure I've got the inside face there. So we'll change that temperature to 95 degrees Celsius to represent that hot liquid running through the inside of the pipe, and click OK. The next load we'll apply is convection, which will represent one of the ways heat is being taken out of the system. So go ahead, right click and repeat that thermal load to add this. If there's a temperature difference between the ABS jacket and the 21 degrees air around it, heat will be transferred between them through convection. How fast this heat is transferred depends on a number of factors, including the surface geometry, material roughness, and if there are any forced convectional forces, such as a fan blowing air over the pipe. These factors are all represented by the convection value. So I'll change the load type to convection and select the outer surfaces of the pipe here. And you'll see we're being asked for this convection value here. Typically for ABS, these values would fall between 5 and 25 watts per meter squared per Kelvin. In this case, I'm going to enter a value of 5 to represent the situation in this particular scenario. However, this value will have a big effect on the outcome of the simulation, and you must adjust this to your part scenario each time. The ambient temperature also affects the rate of heat transfer, so we need to set this in the box below here. We already decided that this was going to be 21 degrees for this scenario, and then click OK to set up that thermal load. Finally, we'll consider if there are any radiation loads. So radiation loads account for energy exchange between the object and the environment, but not across the model, so part to part. So to add those, we'll again add one more load, selecting a radiation load here and the outside of the jacket again. Now, because the material is ABS plastic, we're going to select an emissivity value of between 0.92 and 0.95. So I'll just do 0.92 in this case. And again, that ambient temperature we decided was going to be 21 degrees C, and click OK when you're happy with those. You'll notice that the pre-check here is showing that there's an issue that needs to be addressed before we can solve this study. For effective heat transfer, the components need to know that they're connected. We can use automatic contacts to generate contacts between the three components. In a thermal simulation, the contacts are limited to bonded and offset bonded contact types. Be sure to specify the appropriate thermal conductance value in Edit Contact dialog if you need to adjust this. You can go into Manage Contacts and you can select these if you need to adjust them at all. This action is enough to satisfy our pre-check and we're ready to solve the simulation. Before we do so, I'm just going to refine the mesh. We can generate the mesh down the side here and click View. Pops up with an error saying the mesh has not yet been computed. Would you like to compute the mesh? I'm going to select yes so that I can view it and review if that is an appropriate mesh. If you'd like to explore the mesh settings further, hover over mesh and click the pencil icon. We can see here that we've got an average element size based between 1 and 10%. I'm going to drop that down to 3% here. We can also scale the mesh size per part, select an absolute size, or even go into the advanced settings and explore these. We've got a separate video on this which goes through in detail all the different mesh settings and how they're important to simulation setups. Once you're ready, you can hit solve and solve that one study. We don't need to sit and wait for the study to solve. We can get on with other aspects, say setting up other study types or going back into the design workspace and modelling some other areas. If you need to check the status of your study, we can click on job status and we can check in to see how that's doing. Once the study is solved, we get a notification to say the job has succeeded. We get a green tick here to say the study is complete, and we can head into the results section. It may take just a few moments to fetch the results, and we can now start to explore the results in the simulation workspace. So our default here is to view the temperature output of the simulation results. And there's various different inspection tools that you can use in this study space to help us explore the results. These can be found in the inspection section up here. So you can add minimum and maximum probes to indicate where the minimum and maximum temperature points are across the parts. We can also add in surface probes across the entire surface, so we can look at any point across the surface. We can also add a point probe, which is anywhere within a XY direction. So you could drag that into the center of a part and select a specific XY distance from a particular point. You can also add a cutting plane. So adding a plane across any one of the axes, you can flip the cut direction and you can select the different style that you're using with that. Adding a cutting plane allows us to view the inside of the part, and I often like to use this as a combination of a section plane and then a surface probe, so you can see the surfaces in the middle of the pipe. You can view the cutting planes in the section up here, and you can view whether the visibility is on or off, or you can activate whether the part is cut or not using the tick box here. This is our temperature, and we can select range of temperature we're interested in looking at as well, using the drag handles here or typing in a number of interest. The next set of our results is heat flux, and these are given in a units of power per area unit, for example watts per millimetre squared. And these can be used to understand the performance of the heat transfer through the part or assembly. So you can look at that and change your scale and look at particular areas of interest. We can do this as total heat flux, or we can do this in a particular direction, so in X, Y or Z. Finally, we have our thermal gradient. So with thermal gradient, you can use this to understand the rate at which the temperature is either rising or dropping across your part or assembly. If you have multiple different studies, you can compare them using the compare tool. For example, if you'd cloned the study and set up different materials for that insulation, you could compare the studies to see the differences between your insulation materials. If you've used advanced mesh data, you can view the 2D plot of the convergent data. We didn't use that in this setup here. And finally, we can generate a report. We can use this to generate a report and click preview, which will show this in the web browser. Or you can save the report to somewhere on your device. Once the report has generated, you can view this in a browser. In the study report, it will go through all of the settings that you used in the setup, what materials you've got, how the mesh was applied, your outputs, the thermal load, and those results summary there. You can print a copy of this or save the report to somewhere on your device and share this with others in your team. So there we go. This is a quick step-by-step guide to setting up a simple thermal simulation in Autodesk Fusion. If you've liked this video, please do give it a thumbs up. If you've got any questions, post them in the comments section below, and I'll see you in the next one.